Good evening and welcome back. Let me first remind you what we have done last week. It's a little bit short because I cannot explain everything again, but what was the idea? We have a big and complicated graph. We want to build a tree inside which goes through all vertices, and it's called a spanning tree. And there are different ways to do it. And I introduced two algorithms based on a certain algorithm I introduced before. It's the difference between these two algorithms is the way you choose the next edge for your tree. And so one is called the depth first search. So when you build the tree, you have a graph, you have already a tree TI, and you want to find the next edge to take. So you look at all possible edges that you can take, and you choose one with all these edges in this set front GTI have one vertex on the tree and one outside. So you look at the vertex on the tree, it's called the tree vertex, and they have a index because they have already been discovered. And for this search, you take the one with the largest index. On the other hand, for the depth first search, you do the same thing. You take this front GTI, but you take the edge, the new edge with the minimal index for the tree vertex. And the main difference is with this approach, you explore very far, as long as you can. And then you come back, while when you do the second one, it's more, you start at one point, you explore all neighbors, and then you go to the first neighbors you have visited, explore all its neighbors, and so on. So it's more exploration by neighborhood. But then if you do the first one, I also introduced the notion of DFS pass, which is the long pass you do before backtracking. The last vertex is called XF. And what we observe is that this last vertex has either degree 1, so it's a leaf, or it means that all neighbors are already in the cycle. Otherwise, you could continue. And this is useful for finding the bridge component. If you haven't muted yourself, please do it. So the bridge components, I introduced the notion of bridge on a graph. It is where you can cut and get two separated parts or two components. So the bridge component is exactly the set of components that you obtain when you remove all bridges. And I also introduced the notion of contraction over. Can you mute? Okay, please do it. What was the point? Okay, I also introduced this notion of contraction over bridges. And if you put together both this idea of a DF search, notion of contraction, you get a graph which is a tree. And it is a main structure of the graph. So there is a way to get the main structure or the main shape of the graph by using this algorithm plus contraction over components. Thank you. And then the last part I introduce are, now if you have graph with weights on edges, so it's a kind of graph where you have this additional information, you can either look for the spanning tree with a minimal total edge weight. So you draw a tree, but you want to have the minimal sum of the weights. And there is an algorithm which is quite simple. It's called the Prim's algorithm. There is a different algorithm I also introduced at the end, where you want to find the pass with smallest weight. So by adding the edges, the weights on the different edges. Always it's for a fixed starting point x0, but you want the pass from x0 to any y. And this is a slightly more complicated algorithm, which is called Dijkstra algorithm. There is an illustration of this algorithm and how you can implement it in the notes. It's a rather nice algorithm. And then the application on the picture in the notes is rather nice, I find it. I just wanted to emphasize that these two algorithms do not give you the same thing. Because if you think too quickly, you would think that, oh, it's more or less the same, but it's not true. Think about this very small graph. You have 3 weights. If you want to find the tree with the minimal total weight, you are going to choose this one and this one. So the total weight is going to be 10. On the other hand, so this is what you obtain with the first algorithm. On the other hand, if you look for the second algorithm and you want to go from here to here, you're going to take the second and you don't have the same value. So it means, but it's clear it's not the same because in the first algorithm, you really want to build a tree. So you have to go through all vertices, while for the other one, you want to go from X to Y and you don't care about building a tree. You just want the path with the smallest total weight. So it's not the same idea, and the algorithm indeed do not give you the same result. Okay. If you have any question, you can always ask me. Otherwise, we continue to, the lecture of today is not very complicated and it's quite intuitive. In a sense, it's too intuitive, so we think that it's very easy. A small part is not completely trivial. And by the way, if you haven't submitted any report yet, it's a good time to think about it. We are exactly at the middle of the semester. So please think about it. And we have already several examples on the website. So today it's chapter 5 about connectivity. And again, this notion of connectivity is related to the stability of a graph, how many edges or how many vertices you need to remove to disconnect the graph. And this has many applications. And we already introduced two notions, or yeah. I just recall the names. We have introduced the notion of vertex cut and edge cut. So it was in chapter 2. What we do tonight is again related to this. You can check what was the meaning. And I emphasize that today we have no loop because a loop doesn't play any role. In order to disconnect a graph, a loop doesn't help you. If you cut a loop, it doesn't change anything. So the graphs we consider tonight have no loops. So I need to introduce a few definitions. First, this notion of connectivity. So 5.1, it is vertex and edge connectivity. I need to define what it is. So the first thing is a definition. I take a graph connected. Let G be connected. If it is not connected, you do it separately in each connected component. The vertex connectivity and we denote it by kappa V of G. V is for the, because we deal with vertex or vertices, is the minimum number of vertices so that when you remove them, so whose removal makes G either disconnected or just a one point, so just one vertex, or one vertex graph. So you want to find them, or the definition is the minimal number of vertices that you have to remove in order either to make your graph disconnected or just a one vertex graph. And you can guess the second definition about edge connectivity. Do I have to write it, or I can just cheat? Let me cheat. It's not every day that I can cheat. Edge connectivity, then I need to give a new name, kappa E of G, is the minimal number of edges. Yeah, with a tablet, it's easier for you. You just make copy and paste, and you change 3 words. I cannot do it on the blackboard. And I think it's correct. Yeah, in fact, the last part would not appear. Because if you remove an edge, you also remove the endpoints. No, but you cannot end up with just one point. I don't think you. Yeah. If you have such a graph, you remove the edge. Okay, it's disconnected. So you will not end up with with only one vertex graph. It will make you disconnected, but you will not end up with only one. I don't think you can. So we have these two notions. Vertex connectivity, minimum number of vertices that you need to remove, or edge connectivity is the minimum number of edges you need to remove to get a disconnected graph or a one vertex graph. So we had not, even when we discuss about vertex cut or edge cut, we had not given a name to this notion, the minimal number. Exercise, if you haven't done anything and if you want to play, it's an easy one. There is a relation between these two numbers. Kappa V of G is always smaller than kappa E of G. And it's smaller or equal to delta of G. Do you remember what is this delta of G? Sorry? Say it again. Minimal degree. Minimal degree. Minimal degree. Minimal degree of all vertices. I mean, you look at the degree on all vertices and you pick up the smallest number on your graph. So you can show these two inequalities that this vertex connectivity is smaller than the edge connectivity, which is smaller than or equal. Probably you have many graphs where you have equalities with this minimal degree. You just need to think about it and play, do a couple of pictures, and you will find out how to prove this. Maybe by contradiction. You know, if you have to prove this, you can also try to prove the opposite and get a contradiction. Any question or remark?
The question is, when you're removing a vertex, you need to also remove the edges connected.
Yes, of course. So if you have a graph like this, and you remove this guy, of course, you cannot have edges without one endpoint. This is not allowed. So in fact, when you remove this vertex, you remove these 4 edges. But it was in the definition of removing. On the other hand, and just before I said something slightly wrong, when you remove one edge, you remove this, but still we cannot get a one vertex. No, if you remove the edge, you keep these 2 points. So do it a bigger graph. If I remove one edge, still I need to keep these 2 vertices. Otherwise, I would have to eliminate everything. Because otherwise, if I remove also these 2, I'm obliged to remove this, okay, which is too much.
By the removal of vertex, you have to remove the other. And in which case, for any connected graph, when you do that, you remove the entire graph.
Yeah. So when I remove one edge, I keep the vertices. On the other hand, when I remove one vertex, because I'm not allowed to have one edge without an endpoint, I need to remove the vertex, these edges. Okay. Maybe we can open the window. It's less noisy now. Okay, so a second definition, which is very much related to vertex connectivity and to edge connectivity. So G be connected. When I take a number K, natural number K. So we say that K is K vertex connected. I put a parenthesis because most of the time we don't mention this. So we just say K connected, but the precise version would be K vertex connected. If this kappa V of G is bigger or equal to K. So it means any K which is smaller than this is fine. And now D is, I have to keep it, is K edge connected. I cannot remove it. If kappa E of G is bigger or equal to K. And wait a second, I just do one picture to show you that these 2 numbers can be different. It's quite clear, but let's just check on one example. So if I draw the following graph, and I want to have this, and then many other things. So I don't care what happens here, and the same no matter what happens here. So if I put these 2 lines, I just mean that many things are taking place on the left and on the right. I just want to look at this internal part. What is kappa V? Maybe I should add a few. What is kappa V in this central part? No, it's 2. Kappa V is related. If I want to disconnect the graph, I need to remove these 2. So for this example, if I think that there are many things here and many things here, kappa V of this graph is 2, just on this internal part. On the other hand, kappa E of G, in order to make it disconnected. Ah, okay.
No, still, you remove the upper 2.
No, if I remove the upper 2, it's not disconnected.
Remove the one on the top one and the one to its left. You see a triangle?
I told you there are many things here.
Yes,
and
I
many.
did it in the middle part. There's like a triangle. There's like a triangle and a square, right? You remove
Yeah.
the one on top and one to the left. Still just one and the one to the left. One to its left. Yes. Now the top part is removed.
There's a tree graph that is disconnected from the body
Why is it disconnected?
because it's not connected.
Oh wait, so you assume that the left part, the top left and everything else is connected.
I assume that everything on this is really connected and everything here is connected.
Fine.
Okay, you scared me. So in this case, this is 3, and the thing I need to remove are these 3. If you want to be sure, I add plenty of edges. It's clear now. Okay, so on this example, we can see that these 2 numbers are essentially independent. Of course, in some graphs, they would be linked, but you can play a little bit and obtain different numbers. Okay.
If,
G is K that if. No, thank you. If. So this notion of K connected or K edge connected is rather simple, but it will play a role. And let me just write one sentence related to this because I want to introduce one keyword. So these concepts, the 2 I introduce here, these concepts, they provide an information about what is called the servability, about the servability. And you can guess what it is. It is the fact of surviving when you cut either vertices or edges, or when you remove vertices or edges of the graph. When edges or vertices are removed. It's not a very precise sentence, but we will understand it better in the future. Okay. Now another notion which is going to be linked, and it's a nice notion. Let me just draw a okay. Let's suppose I consider these 2 vertices. There is one notion which is going to be the number of paths between this guy and this guy, which are in a sense disjoint. They have no common internal vertices. So I'm going to define this. You can see that here you would have 2 paths for going from one place to the other one, and they don't have any joint vertices, of course, except the 2 endpoints. So this is the next notion. On the other hand, if I draw another picture like this and like this, then we don't have this. We have a common vertex between this point and this point. So these 2 paths are not disjoint. This is the next notion I want to define. So it's in the definition. I consider X and Y in G, and of course, X is going to, these are vertices. V is always for the set of vertices, and I consider them different. A family of paths, and we know what is a path. A family of paths from X to Y is, oh no, they are internally disjoint and you have to keep in mind the first picture, they are internally disjoint. Oh no, see, it is the family is if no 2 paths of this family have a common internal vertex. Please think about this definition. A family of paths between 2 points is internally disjoint if whenever you take 2 paths, no matter which one in this family, they have no common internal vertex. I didn't define internal vertex, what it means. When you have a path, it's everything except the 2 endpoints. Of course, the 2 endpoints, they cannot be different. So they all go through these 2 points, all passes, but they have no internal vertices in common. Yes. Okay, so this is the notion of, I will even make it slightly more general in the future. And now we have a very old theorem, 92 years old. It's a lemma. I told you things are quite natural today. You will not be surprised. It's called Whitney theorem or Whitney lemma. 22. Would G be connected? And by the way, just observe that I took a path from X to Y because remember, I try always to cover the graphs which are oriented. So it means if for some reason you want to study graph with orientations, you have to really check if your path goes from X to Y with the correct direction. Maybe you have some solutions might not be correct because arrows are going in the wrong direction. So it's really from X to Y. So just observe that it is in the definition. But this, at that time, they were not interested in orientation. So for this theorem, for this lemma, it's unoriented, connected, unoriented, and with at least 3 vertices. G is 2 connected with the definition I gave just before. If and only if. Any pair of distinct whenever you take 2 distinct vertices, so not the same, admit at least 2 internally disjoint. So draw your simplest example, and you will see that this is true. You have to remember what means 2 connected. It means that at least you need to remove 2 vertices in order to make it disconnected, or maybe more, but at least 2. And we can see that this is if and only if any pair of distinct vertices admit 2 disjoint paths. So you have 2 ways to connect these 2, which is quite natural and what you expect. Still, you can try to prove it. There is a more general statement. And I think it's, again, it's not difficult, but it's interesting. I want to generalize this. So let lemma or theorem G, which is this V on E, is connected and oriented and V bigger equal to. By the way, check what happened with 2. I guess it's not correct. I didn't check it. Okay, so the statement is the following: are equivalent. We have several statements which are equivalent. So if you want to show, you have to show that each line contains exactly the same information. The first statement is G is 2 connected, as before. Second one is, if you take any xy inside V, x different from y. There exists a cycle containing x and y. Maybe we will do a picture after. Cycle, remember, it's a path with the same initial point and end point. So it is two connected. You can do a path always containing a cycle containing 2 arbitrary vertices. For any x in V and E in edge, you can do the same. There exists a cycle with or containing both. Let's say like this, containing both. So it means this cycle has to contain both x and the edge E. Now, if you choose 2 edges, this is number 4. For any E on E prime in the set of edges, there exists a cycle containing both. Okay. Number 5, any x, y vertices for any E edge, there exists a path from x to y containing E. Two more. 6. What about 3 point? For any x, y, z in a set of vertices, you can create a path from x to y containing z. There exists a path from x to y containing the third point, containing z. And the last one, which is quite similar. For any x, y, z, in a set of vertices, there exists a path from x to y, which does not contain. It's a long statement, but I think it's quite interesting because you have this notion of 2 connected. You can check what it is, but you have different characterization because these are equivalent, which means each statement contains the same information. So if in your graph, you take any 3 points and you can always go from X to Y and avoid a bad guy, it means you are too connected. Be careful, this statement is for unoriented graph. I can still speak about a path from X to Y, but in this case, it's the same as a path from Y to X. The orientation is not important. Or maybe I should have written a path between X and Y, because it's not important here. So draw a graph which is too connected and check that these statements are correct. And this one is too connected. So you can check before you try to prove. And whenever you have, remember, it's an if and only if. So it means you have to prove equivalences, but one way to prove equivalences is to show that 1 implies 2, 2 implies 3, 3 implies 4, blah, blah, blah. And the last one implies 1. If you show these 7 statements, then you have proved all equivalences, because it means you can go from any number to any other. Okay. Question? What about 3 connected? Which means if you need to remove at least 3 vertices to make your graph disconnected, do you have a similar statement?
Let's start with V greater than or equal to 4.
Good question. Please check if for 3, probably you need a minimal number, otherwise you cannot simply realize your graph. Yes, probably. Yeah, no, nothing. Yeah, but probably there is a minimal number in order to have this statement. So check what is the minimal number, and then what are, I'm not saying that you just replace or add one more guy in all these statements. You have to be a little bit more clever.
Multiple edges?
I don't think it plays a role here. This is exactly what I was thinking. Probably this, I'm completely sure that when the guy, at least in 1932, they were speaking only about simple graph without multiple edges, without loop. I don't think it would matter for this statement indeed.
Yeah, only for this.
Multiple edges, we can have a graph of 2 vertices and these.
Okay, if we do. Check if there is any problem with multiple edges. And if you find a problem, then you write theorem heavy do, and you prove your theorem with multiple edges. I don't think it plays a role here.
2 would work if you need 3 points right there. So 1.
Okay, so this is a typical statement for equivalent characterization of a property. We have 7 different characterizations of a 2 connected graph. And then you can wonder what is the equivalent statement for 3. But so the good point with all this, it means that for 2 connected graphs, by definition, you need to remove 2 vertices in order to separate your graph into 2 disconnected parts. 5.2. It's called Menger's theorem. I can tell you I had a very hard time this weekend with this theorem. There is a simple statement which I'm going to state, but people have tried to extend the statement. And I believe that many proofs are not correct. Even on Wikipedia, I'm not sure that the proof of this theorem is correct. You have really to, it depends on the definitions, but probably you have to be careful. So Be careful if you look at this theorem on internet on different, either on Wikipedia or on other web pages. Some proof, I suspect, are not correct with the initial statement, and I will tell you why. But it can probably be correct. So first, I need to define what are paths between A and B. Because so far I just considered a path from X to Y. I want something more general. So let G, E, B, and E a graph, and I consider A and B two subsets of V. So two subsets of vertices. Okay. Then an AB path is a path from any A inside A to any B inside B with no internal vertex. In A or B. So this is quite clear. Take any point in A, take any point in B. This is a AB path. A path from any point in A to any point in B with no other vertex inside A or B. But then there is already a small question. Oh, if we have one path, or if we have one edge like this, is it considered as an AB path? I mean, there is no other, it's just one edge between A and B. With this definition, it is, but in fact, in the theorem, I'm going to state this is a typical annoying situation. But for this situation, for this definition, this is an AB path, yes. But yeah, this is part of my nightmare. Okay. But at this point, no problem. By the way, it does not always exist. If you have only edges going in this direction, be careful, I'm precise, it's from A to B. If all arrows are going in the wrong direction, or if you have one like this, then one like this, these are not AB paths because you cannot go from A to B. The arrows are not in the right direction. Just be careful about this. So it does not always exist. And now I need to extend the notion of internally disjoint because I did it for 2 points X and Y. Now, what is a family of internally disjoint AB paths? So same framework, G is B and E, and we have A and B inside B. AB paths are internally disjoint. You can guess. You can guess the definition. Take any path in this family, they should not have a common internal vertex. If any two paths from A to B if any two paths from A to B have no common internal vertex. You have a question? So please read the definition before you ask any question. But online, if you have also any question, of course, you can ask. Just unmute yourself. So this is just a natural generalization of the case I considered before. Now you can start at any point in A, go to any point in B, and you look at, you say that these paths are internally disjoint if they have no common internal vertex. Okay. But no, wait, the definition is not correct. Okay, sorry. A family, a family, I should have written like this. A family of AB paths is internally disjoint if any two paths in the family, in the family, I'm not considering all passes because this is never internally disjoint. Sorry, I was not precise enough. A family of AB paths is internally disjoint if any two paths from A to B in the family have no common internal vertex. Now it makes sense. And again, you can wonder, the yellow one, which is just one edge, and the other one, they are mutually disjoint. They have no common internal vertex, because this one has no internal vertex. So you can see that, yeah, we have to be a little bit careful with the yellow guy. And with this definition, you can check that a special case is when A is just 1 point, X, B is just 1 point, Y. It corresponds to what we have seen before. No, if there is nothing bipartite here, please. Last definition I need. What is the notion of separator? The thing is, we want to, in a sense, cut the graph here. But on this picture, it's easy, but things can be more complicated than this. So let G this graph and AB inside V. But observe now I take the condition A intersection with B is empty set. Before I didn't take it because the definition were even fine for A intersection with B, not empty. But for safety, I take it now. A set S inside the set of all vertices is an AB separator. The AB separator. If who can propose a definition? No, you are not allowed. Somebody else. What could be a good definition for AB separator? I want to separate A from B.
S is not in A and not in B. A is not
No,
in
it's
S.
maybe too difficult to guess. If any AB path has an internal vertex. So please think about this definition. Yeah. It's a separator if, so a set is going to be a separator. Let me just draw copper. Oh, no, yes. This is a bad guy. The bad guy annoys me. So let's keep the bad guy here. But this one, this one, this one, and this one, these elements, the blue guys are, it's not unique. I'm not saying that it's unique, but it's going to be a separator because all paths from A to B have a internal vertex in this blue set. This is definition. Check. A set S is an AB separator if any AB path has an internal vertex in S. And you can see the yellow guy is the annoying one because it has no internal vertex. So, okay. Still, the definition is fine, but in the theorem I'm going to state, I will remove the yellow one. Now, there are two natural questions, which are, of course, related. So, determine the following two things. No, this is not, yeah. The minimum number, and I give a name to it, kappa AB of vertices in any AB separator. As I said, the blue points, I can add a couple. Here, the blue set here is still a separator. But I want to minimize the size of the separator. So what is the minimal number of vertices in any AB separator? Okay, this is a natural question. And the second one, which is of course related, the maximal number of, and I give a name, maximum number LAB of internally disjoint paths from A to B. Look, this question, they look quite similar, but still it's slightly different. The minimal number of elements in any separator and the the maximal number of paths which do not have a common internal vertex. And now you can see with these two definitions, the yellow guy is annoying again, and again, because it doesn't really fit well with these two definitions. It's still okay, but later I have to be a little bit careful.
Do we ignore it?
We will see.
Where does it have to go?
Exactly. And then there is one more question. Let me draw. No, I will, after the statement, I will draw one more annoying situation. Do you have an idea about the relation between these two numbers? Sorry?
Smaller.
One should be larger, one should be smaller. They are going to be equal. The statement is that they are equal, but once you have removed this guy or once you have taken care of this one. So let me state one version of this Menger theorem. But there are different generalizations. But so let G and okay, I will write a remark after. Let GV be connected connected, simple. So now simple means there is no multiple edges. I have to be careful about this. Simple and finite graph. I don't want it to be infinity because it's too big. Let A inside both A and B, inside V, A intersection with B empty set. And assume, now this is what I'm going to assume for not having a yellow one. Assume that there is no edge E, no edge E, with one endpoint in A and one endpoint in B. So in a sense, these two sets should not be too close. There is always a certain distance between them. I don't have such an edge. So this sentence is how I remove the yellow one. There is no edge with one endpoint in A, the other one in B. And then now it's they are equal.
There's one, then for the first one, you can just add input number.
Then this number of, define here, this minimal number of edges, of vertices in any separator is equal to the maximal number of internally disjoint paths. So I encourage you to draw a few examples more precise than this one. And you will see that it's quite natural, but still the proof is not trivial. One inequality is always true, you can check, but the other one is not completely trivial. And precisely, you have to be careful about this. You have also to be careful about intersection if A and B have an intersection. So that's why I suspect that some proofs are not correct because they do not state exactly the assumptions. And so a few things you have to pay attention to. What about orientation? I didn't assume any orientation, that the graph is unoriented.
If it's directed, there's no nightmares.
There is still the
Still, yes, the annoying guy can exist even if we have orientation. We can have an edge from A to B. But the statement is still true with orientation. But you have to be a little bit careful with what I said before. You need to consider AB paths from A to B. So you keep the orientation, and the same, these two paths are not AB paths. So the statement is correct even for orientation, but you have to consider really from A to B. But this is not what was my nightmare. What about this? You have to be careful with the definition of separator. Can you guess why I draw this picture? What would be the problem if the definition of separator is not the one I gave you? Can you guess? Wait. Think before you speak. I mean, with the definition of separator, there is no problem. But if I do not define the separator in this way I did it, I could have a problem. Because look, my definition of separator is related to these 2 points. But if I change slightly the definition, by removing this point, I kill all AB paths. So I would have 2 internally disjoint paths. But if I change slightly the notion of separator, by removing this point, I don't have any AB paths. So it means this equality would not be correct. So that's why in the literature, you have to be very careful, check the definition of separator. It's not always the one I have given. And that's why, again, I suspect that a few proofs are not correct. So with the one I have given, I do not consider these 2 points. They are not in any separator. So then the statement is correct for this one. And the same now, if you have this yellow guy, you have to be a little bit careful with the meaning of separator. And again, you can get some contradictions. That's why in the statement, I have assumed that there is a certain distance between A and B. So I just wanted to stress that here. With the definition I have given, the statement is fine. But if you change a little bit the definition of separator, or if you don't impose a distance between these two sets, I'm not saying that there is no possible statement, but you have to be careful. And people have tried to generalize this statement, but I'm not sure that it's always correct. And again, the proof is not trivial. You can check in any book, it's always at least 1 page, or it's not too short. Even though if you draw it on a picture, you will see that it's quite natural. Corollary, which is an easy thing. G connected. Simple. Unoriented. Now I take it unoriented. G connected, simple, unoriented, finite. With at least X, Y in V, not connected. So it means I assume that there are at least 2 vertices which are more than at a distance 1. Otherwise, my statement is not correct. Then kappa V of G, which I have defined, is vertex connectivity, is a minimum over XY. Oh, that's right. Non-adjacent. This is rather straightforward. You need just to check the definition. Remember, the connectivity, vertex connectivity, is a number of vertices you need to remove in order to disconnect your graph. It's given by this kappa of X, Y. What is it? Remember, just before I introduced kappa of AB as a number, as a minimum number of vertices in a separator. And now I just take A is 1 point X, B is 1 point Y. And if you think about what is the meaning, you get that this minimum number for any point X, Y vertices not adjacent, because in order to apply this theorem, I need to consider things which are not adjacent. Then you have this equality. And there is a second corollary, which is also completely natural. but it's good to state it. By the way, if somebody wants to check these two corollaries, the proofs can be done as an exercise. Okay, same assumption, D connected, simple. Heavido, you can check that these these statements are not correct if G is not simple. G connected, simple, unoriented, finite. Then G is K connected. It means kappa, the kappa V of G is bigger than K. G is K connected if and only if for any XY vertices, X different from Y, they exist at least K internally disjoint paths. From X to Y. Maybe you have the feeling that I'm just turning around the same notion. It's indeed the case, but we have different views or different relation between the same objects. It's always linked to the stability of a graph with respect to removing edges or removing vertices. And if it is K connected, it's if and only if, it means that you have K disjoint, internally disjoint paths from X to Y. So essentially, this is again Menger's theorem. Just think about it. I encourage you to do a few pictures. There are a few pictures in the notes. You can check what is the meaning on these examples. All right, there is a last section I want to present today. And so we have finished with this section, this chapter 5, and move to something else. We had already last week or 2 weeks ago. No, it was last week. If we have a complicated graph, but some bridges, this is a bridge, this is a bridge. We had already seen that we can contract and get a kind of skeleton from our graph. So it's the structure is presented, only the main structure. You remove the details and you get the structure. It was with contraction, but look, this definition had a small problem with multiple edges, because now this is not a bridge. Oh, sorry, yeah, this is no more a bridge if you have two multiple edges, so you wouldn't contract. So the next construction is again about getting the main structure of the graph, but it's slightly better from a point of view of multiple edges. This is what I wanted to see. So this is called 5.3 block cut point. I need to explain what it is, but it's very much related again to the main skeleton of the graph. ID get the main structure. Which is also called skeleton of a graph. It's a slightly different construction. So first, I need to give a definition for what is a block. A block of an undirected, there is no orientation, undirected graph. Block of an undirected graph G. Is a maximal. So it's a maximal connected subgraph which does not contain please look at this definition. I will draw a picture. So let me draw a picture. Okay, so we look for blocks. So block is a subgraph connected, which does not contain any cut vertex of the block. So this is a block. I cannot extend it further because if I want to include this one, I would have a cut here. Oh, maybe I have a second one here, but that's not all. I have additional ones. This is also a cut, block, sorry, and we have one more here. We have 4 blocks. And by the way, observe, I just drew a second picture. I want to be sure about one situation. If we have a double edge, the situation is different. Because in this case, I guess we have only 2 blocks. I suspect that this is one block. Oh, no, this is not. No, this is not correct because this is not correct because if I remove this guy, I disconnect it. So no. Okay, so this is not correct. I need to keep the same block structure. In fact, the block structure is the same. It doesn't, yeah, that's the difference. It doesn't really see multiple edges. And we have one here. And oh, sorry, I thought it was different, but no. The block structure is the same no matter if we have a multiple edge here, because it's only related to vertices. Okay, this is definition of a block. What do we observe? First, observe that a block can contain a cut vertex of the full graph. This guy, this is a cut vertex of the full graph. If I remove it, the graph is disconnected, but it's not a cut vertex of the subgraph. Yes.
block made of one box, a smaller box.
Has to be connected. So it's one piece. It cannot be two disjoint pieces. So I guess it's always made of, it's a connected part. But yeah, first observation is a block can contain a cut vertex of the big graph, but by definition, it doesn't contain a cut vertex of the small part. So this is an observation. Or maybe it's going to be even in this next statement. So maybe write it as an observation. Yes. A block can contain a cut vertex of G. There is no contradiction. It have not to should not contain a cut vertex of the subgraph, but it can contain cut vertex of the big graph. This is the first observation. Now, the second one is about a block. You don't have so many possibilities. A block is either, we have three solutions. Oh, by the way, do you remember what is maximal? I didn't mention it. Maximal is you cannot find one which is bigger and has the same property. So, for example, if you just consider this could be a block, but it's contained in a bigger one. So maximal is always the biggest one with some property. So a block is either a maximal two connected, and now we know what is two connected. It's either a maximal two connected subgraph with at least three vertices. And indeed, we have two guys like this in this picture. So this is the first case. The second case is the yellow, these four yellows guys. So the second one is what is called a dipole. So what is it? It means two vertices and at least one edge, or maybe more than one if you have more than one. This is called like this. And what is the third option? A poor, lonely guy. The third option is a single vertex, an isolated vertex. So 1, 2, 3. Isolated. So you can check, and this is probably interesting, do more pictures and check that you have only three solutions. Now, another statement which is not difficult to check, if G is undirected and without loop, I accept multiple edges, but no loop. What do we observe between blocks? They always intersect at one vertex. And this, look at look at the intersection. They always intersect at one vertex, and what more?
That vertex outward.
Right. These yellow points so these intersections are always just one vertex. But in addition, if you cut them, you disconnect the initial graph. So this is the first observation or the first part of the lemma. Any two blocks can only intersect at cut vertex of the initial graph, G. What about edges? Look, edges, they always belong only to one block. Edges only belong to one block. What about cycles? Okay, we don't have so many, but cycles, if you think about, yeah, if you take for granted these three alternatives, cycles have to be, okay. Yes, this is a cycle. Yeah, this is fine. This is a cycle, but it's in one block. So there is no contradiction. Cycles are within blocks. Again, think about, draw a few examples and you will see that this has to be true. But it's not a proof yet, but you can prove this. And okay, now what I want to do, remember, I want to get the skeleton of this graph. So I'm going to construct something which contains just the minimal amount of information about this graph. I cannot do a bigger and complicated graph, but if you look at the notes, it's probably do it later. On the last page of section or chapter 5, you have a more complicated example which tells you exactly what I'm going to present now. So I encourage you to look at this example because this one is a little bit too simple. But again, the idea is I'm going to take only the main information about this graph, and I'm going to create a tree which is bipartite. Remember, a tree or something which is bipartite means you always have a connection between a blue dot and a red dot, but never between two red dots or two blue dots. So you can color with two colors. So I start with any graph G. I do this construction by block. And then I realize what is called a block cut point. Tree, because it's going to be a tree of G, which is VE. This is my initial graph G, which is VE. So what is this block cut point tree? It's a new graph, which I'm going to call the graph WF. So this is for the set of vertices. This is for the set of edges. With, if I want to get, I can already emphasize here, a bipartite tree, it means a set of edges can be divided into two parts. So W is going to be W1 union W2. and they should have no intersection. So remember, I probably introduced once this notation when you have two sets, it's a union, but they have no intersection. This is called a disjoint union. Disjoint union. It's a union, but without any intersection. So I need to define what is W1, what is W2. So with X belong to W1, if X represents a block of G. So it means each block is going to be represented just by one element in W1. So in particular, on this example, I'm going to have 4 elements in W1. Now I need to define the element of W2. Can you guess what are going to be the element of W2? The cut points of the big graph. So the intersections, more precisely. So W2, Y belong to W2 if Y represents an intersection of blocks I guess we can have an intersection with more than, yes, more than 2. So again, points in W1 are going to represent blocks. Points in W2 are going to represent intersection between blocks. And now I need to so I define who is W1, who is W2. Of course, they are disjoint because a block is different from an intersection. That's clear. That's clear. What is F? The elements F. What are edges? Edges is this guy belong to this block. So I can draw an edge between the Y, which is this point, and the X, which is this point. So E belongs to F if E represents the represent, let's see, one intersection of blocks inside a block. Okay, I'm not sure I can do it, but let's try to realize this cut point tree for this graph. I didn't try, but let's try. So we should have four, let's say, yellow points. I don't know if I need to organize them in any way. Because we have 4 blocks, I need to have 1, 2, 3. Okay, it's easier than what I said. 1, 2, 3 red points. So W2 is made of 3 points. W1 is made of 4 points. And what about edges? This guy is between these 2, then, okay, this is easier than I expected. In this case, this is the simplest tree. But as I said in the notes on the last page of section 5, chapter 5, you have a more complicated example. And it's interesting to see that, yeah, the main structure of this graph, which is rather complicated, it has double edges or multiple edges. You can encode it in a single bipartite tree. So if you want to, it's always the same thing. You have something complicated. You want to extract the information. How you do it systematically. We had seen one approach with contraction over bridge components, but this has a small problem with multiple edges. On the other hand, this construction has no problem with multiple edges, and it still gives you one tree, this one is very simple, but already the one here is less simple. It gives you one bipartite tree which encodes information in the graph. So you extract the main structure. Okay. So if you want to summarize, it's always good to take a step back. This subject about graph theories, not so difficult because many definitions are natural, but it's important to give a definition to notions. Whenever you have a certain object, you have to be precise, give definitions, and then make connections between these definitions. And if you look at this subject, it's mainly we define precise notions, and then we make connection between these notions, and proofs are usually not very difficult. But it's important to have precise definition and to take care of special cases like the yellow guy I mentioned before, which was directly a link between A and B without internal vertices. So you have to check this special situation. Okay, that's all for today. Next week, we start chapter 6. I will put it on the website soon.
What about the lonely guys? They can also be a block, but there are no interesting.
Then this is this lonely guy. So first, it's a separate picture. Check. It's a block itself. So it's going to be one element in W1. What about W2? You have no you have no intersection of blocks, so there is no element in W2. You have no edges, so the graph corresponding to this guy is this guy itself.
The tree will be disconnected, right?
No, but I started probably with a connected. So, okay, it was two different situations. So the construction corresponding just to this guy is this guy itself, the simplest tree. Okay, and I assume that I had no loop, so I don't have the situation with this guy on the loop. Any other question here or online? If you have any question, you can always ask.